Molecular interaction studies on binary liquid mixtures of ethyl oleate and ethyl methyl ketone at temperature range from 303.15 K to 318.15 K. Abstract, density, dot, ultrasonic velocities, U, and dynamic viscosity, dot, for binary mixture of ethyl oleate with ethyl methyl ketone is experimented at ambient temperature range from 303.15 K to 318.15 K at atmospheric pressure over various compositions. The density, dot, and viscosity, dot, are calibrated using specific gravity bottle and Ostwalds glass capillary viscometer respectively. The velocity, U, is measured using ultrasonic interferometer. The thermodynamic parameters such as internal pressure, pi, free volume, Vf, molar volume, Vm, and acoustical parameters such as adiabatic compressibility, Ss, intermolecular free length, Lf, acoustic impedance, Z, relaxation time, T, and their excess parameters have been calculated. Keywords: ultrasonic velocity, density, viscosity, adiabatic compressibility, free volume, internal pressure, molecular interactions. Introduction. In our earlier investigations, 1 to 2, we made an attempt by making use of an ultrasonic technique to explore the behavior of some of the amino acids as well as in organic liquid mixtures. In recent years, much effort has been made with measurement and interpretation of the ultrasonic properties of liquids and liquid mixtures. The ultrasonic studies are of great importance in helping to understand the nature and extent of the patterns of molecular aggregation that exist in liquid mixtures, resulting from intermolecular interactions 3 to 4. There has been an increasing interest in the study of systems comprising of unlike components with interactions of varying type. The sign and magnitude of excess parameters have been used to investigate the interactions between the components of a system 5 to 7. Molecular interactions are interactions between electrically neutral molecules or atoms. Other than atomic bonds, these are electrical in nature and consist of attractive forces, orientation, induction and dispersion forces, and repulsive forces. Molecular interaction first taken into consideration by J. D. van der Waals, 1873, in explaining the properties of real gases and liquids. These depend on the distance between the molecules and usually are described by the potential energy of interaction. Studies on liquid-liquid mixtures, either binary, ternary, or more, has importance of its own in various fields of contemporary civilized societies like chemical engineering, food processing, preparation of cosmetics, polymer paints and cleansing agents, petroleum, edible and non-edible oil, preparation of biodiesel, etc. Ultrasonic waves have their extensive applications in various fields like non-destructive tests for solids and liquids in medical and engineering, food processing, pharmaceutical, polymer and chemicals, metallurgical industries, etc. It will be an advantageous tool if these two fields were combined for conducting studies on inter- and intraparticulate behavior. Ultrasonic investigations of binary mixtures have been taking place since decades by so many scholars under various heads like acoustic, thermodynamic, molecular interactions, etc. The thermodynamic studies of binary liquid mixtures have attracted much attention of research scholars and scientists, and experimental data on number systems are available from review and publication 8 to 12. Ultrasonic investigation of liquid mixtures consisting polar and nonpolar components is of considerable importance in understanding intermolecular interaction between the component molecules, and they find applications in a number of industrial and technological processes. Many investigations 13 to 18 have been employed in the task of collecting more and more data and explaining in terms of the properties of pure liquid. In the present paper, the authors submitting part of the studies as the effect of temperature and concentration on ultrasonic velocity, V, of 2 MHz wave in the pure and mixtures of two organic liquids ethyl oleate and ethyl methyl ketone at various temperatures 303.15 K, 308.15 K, 313.15 K and 318.15 K. The effects on density, dot, viscosity, dot, adiabatic compressibility, SOD, intermolecular free length, LF, and internal pressure, I, also were studied. Results were tabulated and the relations among the mentioned parameters were represented as graph .1-24. Materials and experiments. All the materials procured are of Sigma Aldrich AR grade and glassware used of borosilicate make. Organic liquids ethyl oleate and ethyl methyl ketone were procured are used directly without any purification. The densities and viscosities of the liquid compounds were measured with specific gravity bottle and Ostwald viscometer pre-calibrated with 3D19 water of millipore to nearest mg/ml. The time taken for flow of viscous fluid in Ostwald viscosity meter is measured to a nearest 0.01 second. Borosilicate glassware, Japan make Shimadzu electronic balance of sensitivity plus 0.001 gm and constant temperature water bath of accuracy plus 0.1 K were used while conducting the experiments. 2 MHz ultrasonic interferometer model No. F05 with least count of digital micrometer 0.001 mm of Mittal Enterprises 20 was used for calculating velocities of sound waves and all the tests were conducted as per ASTM standard 21 procedures. The 30 ml of binary mixtures of ethyl oleate and ethyl methyl ketone were prepared with variable volumes of 5 ml each to conduct the experiments from which the mole fractions were calculated 22. Theory and calculations. In order to examine the intermolecular interactions in liquid mixtures of ethyl oleate with ethyl methyl ketone, experiments were conducted to find the density, viscosity, and velocity of 2 MHz ultrasonic waves for pure liquids and for binary liquid mixtures. The results of pure liquids are compared with literature values for assessment. From the experimental data of binary mixtures, the derived and excess values were calculated at various mole fractions of ethyl oleate for understanding the inter- and intramolecular interactions at each temperature. The derived and excess values are calculated by using the following relations. Adiabatic compressibility, SOD. Adiabatic compressibility. The parameter which represents the ability to change volume of a liquid sample is intermolecular free length, LF. The formula for outer-to-outer distance between the interacting molecules. Molar volume of the binary liquid mixture, Vm. The molar volume of the system at every mole fraction for the mixture is given by free volume, Vf. The free volumes of the binary mixtures have been computed using its relationship with the ultrasonic velocity and viscosity as given below. Where K is a constant, which is independent of temperature and its value is 4.28 x 109 for all liquids. The ultrasonic velocity is influenced by the acoustic impedance, Z, which is given by the relation excess thermodynamic parameters. With the help of excess parameters, the extent of deviation from the ideal behavior of binary mixture can be estimated. The difference between the thermodynamic function of mixing for a real system and the value corresponding to a perfect solution at the same temperature, pressure, and composition is called the thermodynamic excess function, denoted by YET. Excess value YET for each parameter can compute by using the general formula YET equals Y, Y1x1 plus Y2x2. 6. Where Y is the parameter under consideration, x1 and x2 are mole fractions of two liquids ethyl oleate and other organic compound under consideration respectively of the binary system, ethyl methyl ketone here and E represent excess deviation in adiabatic compressibility, SOD. The difference of the adiabatic compressibility of the mixture and the sum of the fractional contributory adiabatic compressibilities of the two liquids individually is the deviation in adiabatic compressibility. At a given mole fraction it is given by excess free length, LFE. The excess free length can be calculated with formula excess acoustic impedance, ZE. Excess acoustic impedance can be calculated by the relation results and discussion. Velocities of 2 MHz ultrasonic wave, densities, and viscosities of pure ethyl oleate and ethyl methyl ketone were measured with pre-calibrated interferometer, specific gravity bottle and Ostwald viscometer respectively in the temperature range of 303.15 K to 318.15 K. The results were compared with available literature and shown in Table Point 1 and Table Point 2. The experimental values of density, viscosity, and speed of sound, U, for all the mixtures over the entire range of composition, and at 303.15 K, 308.15 K, 313.15 K and 318.15 K are presented in TABLE3, TABLE4, and TABLE5. In order to examine the intermolecular interactions in liquid mixtures of ethyl oleate with ethyl methyl ketone, experiments were conducted to find the density, viscosity, and velocity of 2 MHz ultrasonic waves for pure liquids and for liquid mixtures. The results of pure liquids are compared with literature values. The experimental values are coinciding with the values from the previous studies. The derived, excess values were calculated at various mole fractions of ethyl oleate for understanding the inter- and intramolecular interactions at each temperature. Graphs were drawn for variation of the experimental and derived quantities with mole fraction of ethyl oleate at all the study temperatures as shown in Graph 1 to Graph 24. From the above studies it can be concluded that there exists a dipole-dipole interactions among the unlike molecules. In the above system the experimental values are changing gradually from values of selected organic compounds ethyl methyl ketone at x1 is 0.0000 to the values of ethyl oleate at x1 is 1.0000. In addition to the shape, size, and dipole moment of the molecule, the main contributions to the excess properties to the mixture of liquids are I. Physical like weak van der Waal type, 2. Chemical like strong hydrogen bonding, and 3. Structural like interstitial accommodation 8 to 9. The experimental values of the velocity, u, density, dot, and viscosity, dot, decreases with increase in temperature and increases with increase in mole fraction of ethyl oleate at constant temperature. The derived parameters adiabatic compressibility, SOD, intermolecular free length, LF, molar volume, VM, are increases with increase in temperature, and there is no considerable change in the values of Rao's constant, R, and Watta's constant, W. The thermodynamic parameters free volume and Gibbs energy are increases with increase in temperature, and acoustic impedance, internal pressure, enthalpy, and relaxation time are decreasing with the increase in temperature as shown in Table 4. Except internal pressure, all other parameters shown in the same table are increasing with the increase in mole fraction of ethyl oleate at given temperature. The excess parameters explain the nature and strength of molecular interactions shown in Table 5. The excess velocity, UE, deviation in adiabatic compressibility, SOD, excess intermolecular free length, LFE, excess acoustic impedance, ZE, excess molar volume, VME, excess free volume, VFE, deviation in viscosity, excess internal energy, .E, excess Gibbs free energy, .GE, and excess enthalpy, HE, are calculated and presented in this chapter. The excess values are 0 for pure compounds. It has been reported 31 that excess values of the binary mixtures result from the contributions due to the physical, chemical, and structural characteristics of the component liquids. The physical contributions comprise of dispersion forces and nonspecific physical, weak, interactions, which lead to positive VME and SOD values. The chemical contributions involve breaking up of the associates present in the pure liquids, resulting in positive VME and SOD values. These chemical contributions also involve specific interactions such as formation of H-bonding, charge transfer, donor-acceptor, complexes, and strong dipole-dipole interactions between the component molecules of the mixture, resulting in negative VME and SOD values. The structural contributions are due to the geometrical fitting, favorable/unfavorable, of the molecules of very different molecular sizes into each other's structures, resulting in negative/positive excess values. In the present investigation, the excess adiabatic compressibility, SOD, the excess free volume, VFE, excess free length, LFE, exhibit negative values over the entire range of composition at all temperatures studied, clearly indicate the presence of strong interactions 32 to 41 between ethyl oleate and ethyl methyl ketone. Further, the excess internal pressure, P, which is usually explained in terms of molecular interaction, whose negative excess values suggest that strong molecular interaction between the unlike molecules 40. The variation of experimental, derived thermoacoustic and excess parameters with change in temperature and mole fraction of ethyl oleate are shown as graphs from graph point 1 to 24. The excess values those explain the nature of interactions for the system are shown in relevant table 5 for mixtures of ethyl oleate with ethyl methyl ketone. The excess values are 0 for pure liquids. The negative excess values indicate the strong interaction, whereas the positive shows the relatively weak interactions 42 to 44. Positive values of excess velocity and excess viscosity represent strong interactions. Except the excess velocity, UE, excess acoustic impedance, ZE, excess viscosity, excess Gibbs free energy, .GE, and excess enthalpy, He, remaining all the excess parameters for the binary mixture for the system is negative. Conclusions. The ultrasonic velocity, density, and viscosity measurements have been carried out for determination of ultrasonic parameters for the different composition range of ethyl oleate and ethyl methyl ketone at different temperatures, viz. 303.15 K, 308.15 K, 313.15 K and 318.15 K. The negative values of SOD suggest that the binary liquid mixture is less compressible than the corresponding ideal liquids, and the positive values indicate the reverse actions. The maximum negative values of adiabatic compressibility, SOD, are -1.1584, -1.1670, -1.3522, and -1.4837 at the 4 temperatures under study. The negative excess values of molar volume, VME, and positive excess values of viscosity, shows the molecular interaction between ethyl oleate and ethyl methyl ketone due to dipole-dipole molecular interaction. Acknowledgements. The author is very much thankful to UGC for sanctioning fellowship, which financially helped for procuring instruments and chemicals, Andhra University for providing infrastructure facilities.